Hi everyone. In this video I am going to explain about receiver noise. So what do you mean by noise? Generally noise is treated as an unwanted signal. So generally noise is nothing but unwanted signal. Okay. Now in this pulse radar system where the noise can present, how this noise can affect the original performance of the radar range equation. Okay, this is the second important concept which affects the radar range equation. The first one is the minimum detectable signal. Yasmin, I have explained in the previous video. Now this is the second important topic which affects the radar range equation in terms of noise. Okay, now so noise is treated as the unwanted signal that presents in the receiver at any stage. In the receiver we have several blocks from the right from the beginning of antenna. Immediately after antenna we have amplifier. Okay, low noise RF amplifier, after that mixer, after that IF amplifier. Several stages are there. Among all these stages a receiver noise can add at any place. Okay, so now let us see, this noise can be added from antenna terminals. It can be added from antenna terminals, nothing but from environment, external environment. When we are receiving the signal from any object, the received echo signal may consist noise and that enters into the receiver. Okay, that is from antenna terminals, or it can be generated, the noise can be generated within receiver. Okay, that means there are two types of noises that can be presented in this receiver noise. So one is within the receiver, it can present, it can generate because of the several devices we are using in the radar receiver system, or it can also, the noise can also enter from the external environment through the antenna. Okay, suppose if we are assuming one condition that my receiver is completely pure from noise. I have designed the complete receiver with good contacts, good contacts, and every components we are using very neat and clean components, and no noise is there. And the antenna environment which I am using the radar signals is also very pure and no noise is there. Suppose if I am assuming everything is ideal condition. In such case also some noise is there because of ohmic portions of receiver input stages, because of ohmic portions of receiver input stages. So that receiver input stages is due to heat, so because of this heat, noise is generated, noise is generated at receiver input due to ohmic portions of receiver. So at the receiver input stages, because of the ohmic portions, some noise is generated because of this heat. So such type of noise is known as, such noise is known as Johnson noise, or mainly known as thermal noise. Okay, so Johnson noise or thermal noise, it is the noise due to thermal contacts of the receiver input stages. Ohmic contacts because of their heat at the receiver input stages. This noise is known as Johnson noise or thermal noise. Thermal is nothing but heat. Thermal is nothing but heat. That's why it is thermal noise. Okay, how can you express this thermal noise? How can you write the equation for this thermal noise? So thermal noise is proportional to thermal noise is proportional to, so thermal noise is proportional to what are the what factors it depends on? Temperature, temperature of operation at that particular time, and bandwidth of receiver, bandwidth of the receiver. So what is the bandwidth of the receiver in the entire several blocks of the receiver? In the receiver, we have several blocks, right from the, I told you already, right from the beginning of low noise RF amplifier till the end of display section. Okay, I am just giving the introduction. What are the blocks we have in the pulsar radar system? If you have any doubt, you can go back and see. First, we have a receiver input. At the receiver input, low noise RF amplifier, followed by mixer, IF amplifier, and next detector, after that VD amplifier, threshold, and then display. Okay, among all these, which is the deciding factor of the bandwidth for the receiver? Which is the deciding factor of the bandwidth for the receiver? That is nothing but IF amplifier. That is nothing but IF amplifier. So IF amplifier is the main bandwidth deciding factor, which gives the overall signal, the how much signal that enters into the receiver, how much signal that eliminated from the receiver, that completely dependent on the bandwidth of the IF amplifier. Okay, so bandwidth of IF amplifier is nothing but bandwidth of receiver. Note here, you need to note down one point. Bandwidth of IF amplifier is bandwidth of receiver. Bandwidth of IF amplifier is nothing but bandwidth of receiver. So now thermal noise is proportional to temperature into bandwidth of the IF amplifier. Here bandwidth I am representing it as Bn. Bn is nothing but noise bandwidth. Bn is nothing but noise bandwidth, where what is the amount of noise that enters into the receiver, that is purely dependent on the IF amplifier. So that's why Bn, noise bandwidth. If you remove this proportionality constant, it becomes KTBn. Okay, KTBn. K is nothing but Boltzmann's constant. What do you mean by K? K is nothing but Boltzmann constant. T is the room temperature, and Bn is nothing but noise bandwidth. I am writing here K is nothing but Boltzmann constant, Boltzmann's constant, and T is nothing but temperature, room temperature, and Bn is nothing but noise bandwidth, noise bandwidth. Okay, this is what the thermal noise is proportional to. So thermal noise, you can write it as simply thermal noise is nothing but thermal noise is equal to KTBn. KTBn. So temperature, it is in terms of 290 Kelvin. 290 Kelvin. You know the Boltzmann's constant. Boltzmann constant, how we can write? It is around 1.38 into 10 power minus 23. Boltzmann constant is given by 1.38 into 10 power minus 23. Okay. Now, K is a constant. T is nothing but it's a value like a 290 Kelvin. Coming to Bn, how can you write the expression for Bn? How can you write the expression for Bn? Noise bandwidth. So Bn is written as Bn is equal to integral minus infinity to infinity h of f mod square divided by h of f naught square into df. What do you mean by h of f and what do you mean by f naught? H of f is nothing but filter response, filter response of IF amplifier, filter response of IF amplifier. and f naught is nothing but it is the frequency, where the response is maximum. Okay, suppose I am having a frequency response like this. It is the frequency IF amplifier frequency response I am drawing now. It is the gain. Okay, so it is mod h of f. Now 0. This is having a frequency response like this. So see this, it is f naught. So f naught is a point of frequency at which the response is having maximum gain. This is what the bandwidth of IF amplifier. So noise bandwidth, you can say this as noise bandwidth. Bn can be given, can be written as Bn is equal to integral minus infinity to infinity h of f square divided by h of f naught square into df. Okay, if h of f is normalized to unity at mid band, then h of f naught is equal to 1, the bandwidth of an equivalent rectangular filter whose noise power output is the same as the filter with the characteristics h of f. Okay, that means suppose if it is normalized, then simply it becomes 1. H of f naught becomes 1. If normalized means it is having unity characteristics. Okay, now this is what the noise bandwidth, and thermal noise is nothing but the noise which is present at the input of the receiver input stages because of the ohmic portions heat present over there. Okay, that's why as the heat is produced and the noise is generated, because of that it is termed as thermal noise. Okay, now I will explain the noise figure, how it is affecting and adding in the radar range equation or max in the next video. Okay, thank you.